All right, it is 6 o'clock, or whatever time it is where you are. So we will get started. Welcome to lecture 4 of Vector101. This is a code lecture, and we'll be coding some things related to vector geometry that we talked about on Monday. And before I get started, I'm going to give these reminders again as I did last week, and I'm going to continue to give these reminders because they're so important, which is doing the exercises for one. Like, this is how we learn. We don't learn in lecture. We learn from doing exercises. And then 2, come to office hours if you need help. Office hours are on Saturday at 1 p.m. Pacific time. All right, now our agenda for today. So the first thing we're going to do is we're going to tidy up some work that we did last week. So some of the folks who did their homework alerted me that I forgot to implement a couple things in lecture. So we're going to do that today. And then we're also going to do some geometric methods for vectors, and then we'll implement the Gram-Schmidt algorithm, and then finally we'll do some coding for subspaces. And then I'm changing up the format a little bit from last week. So last week we did like a whole chunk of math and then a whole chunk of code. And this week I'm going to try something a little bit different. We're going to interlace the two of these. So we're actually going to jump right into the code. And this week we'll be in Roblox Studio. I think this is better than Sublime because if Sublime, well, everybody is comfortable with Roblox Studio. So we'll just use Roblox Studio. Let me switch which screen I'm sharing. All right, here we are in Roblox Studio, and this is our vector class that we worked on last week. So there's something, right, yes. Okay, so something to notice that's new is that I've filled in the homework methods. So your homework was to add the cross product and add magnitude, and so here they are now, and they're also updated on the repository on GitHub. And so I'll be doing the same thing this week, where, I'll add the homeworks in a week after I sign it. All right, so these are the new methods, and then as far as the tidying up for a vector class goes, I'm just going to show you because it's not really worth going through. It's pretty similar to what we did last week. So one thing that I added, well, first I should go through a fix. So I actually explained the is vector wrong last week. I had a bug in the code. This is what it should be. We're checking that something is a vector by making sure that its meta table is the correct MT meta table. And then something else I added was this vector.0 constructor. So this is creating a vector of all zeros of a given dimension. Some of the students did this for their homeworks, and I thought this was a really great idea, and we're actually going to use it. So I added it myself. So thank you guys if you did your homework and asked for feedback. And then something else that I had forgotten to do last week was div. So we did scalar multiplication, which we can do with this mul function, but I forgot division, which is dividing a vector by a number. And what's easier about division actually is that you can't divide on the left. So like we cannot do a number divided by a vector. This is like not a defined operation. So it's a little bit easier than multiplication, where we only have the case where it's a vector divided by a number. And so that's what you see here. We divide each coordinate by the number, and then we return a new vector. And in the case where b is 0, I didn't actually put that in. I should probably do that. But when b is 0, we can't divide by 0. And so we should probably error there. And then the last thing I added, which I forgot about, was very important, vector equality. How do we equate two vectors? Well, we equate their individual coordinates. And so that's all this is doing, is it's running through each coordinate. And if any of the coordinates are not equal, then we return false. And otherwise, if everything goes through correctly, then we return true. So these were some of the things that I forgot last week. So now we have them. Next, I will switch back over to my tablet. Can div, so this is a good question from Borb. So Borb asks, can div just be written as a scaling by the reciprocal of the scalar? So could div just be like return A is the vector A times 1 over B. And the answer is yes. Maybe there's like a little bit of a performance boost from inlining it instead of calling another function, but you are correct. All right. Right. I was going to switch back to my tablet. All right. So this gets the first task out of the way. In the second, we're going to talk about some of these geometric methods, and we're going to start with magnitude. And we know what the magnitude is. We use it all the time in Roblox, but maybe we don't know how to compute the magnitude by hand. And when we talk about the magnitude, what we mean is like the length of an arrow. We talked last class about how vectors are like fundamentally just arrows, and the magnitude is the length of this arrow. And we define the magnitude to be this, to be the square root of the scalar product of x with itself. And on Monday, Aiden went through an analogy of like, well, this is kind of the same thing as the absolute value of a scalar being the square root of itself squared. And I'm going to give you a different reason for why we define the magnitude this way. So we're going to run through an example. So here we have x. This is a two-dimensional vector, and so we're going to just compute by hand its magnitude. So looking at a formula above, its magnitude is going to be the square root of the inner product of x1, x2. And then we'll inner product it with itself, x1, x2. And then close the square root. All right, now let's write out the inner product. So this is going to be x1 times x1 plus x2 times x2. And then lastly, I'll just rewrite it in what should look a bit familiar. So in this form, what we see is that this looks a lot like the Pythagorean theorem. And let me mark this out on the diagram. So given our vector x, so it's this down here is going to be x1, on the right this is x2, and then the whole thing is the magnitude of x. And we see that from the Pythagorean theorem, like this is the Pythagorean theorem, which is right. I don't think there's much else to say there. So that's like another way of thinking about where this magnitude computation comes from. And now, once we have magnitude, we can talk about unit vectors. So in the same way that we can take any non-zero real number and we can multiply it by its reciprocal to get 1, we can do something very similar for vectors. And for vectors, what we do is we take a vector, a non-zero vector, mind you, and we multiply it by the reciprocal of its magnitude. And then we look at the magnitude of this entire thing, and this should be 1. So it's analogous to what we do for numbers. And actually, if you did your, I think this was a homework question last week. The reason like this works is right. So this is going to be equal to, we can just pull this out, and then this is just the magnitude of x. Okay, and so this is 1. And so, well, now it's gone. But that is a fact that you proved in your homework. So in a sense, what we're left with is just information about the direction of x. Like the magnitude is still there. Okay, it's not gone. It's 1, but like 1 is it's like the most neutral magnitude. Maybe I'll say. Like really, what we care about is just that it has a direction. And so this is why we use unit vectors for like a C-frame dot look vector. Like we don't care about the length of the look vector. We just care about the direction. Right. So this is our definition of a unit vector, is that it's a vector with magnitude 1. Okay, so now that we have magnitude and we have unit vectors, we can reinterpret the scalar product. We talked about the scalar product in the first week. We're going to talk about it again here. And on Monday, Aiden went through a very good scheme about like the Graham-Schmidt and this sort of thing. But we're just actually going to skip to the upshot, which is that the scalar product encodes information about the angle between two vectors and the magnitudes of these two vectors. So this is what we saw on Monday. We have the inner product here, we have the magnitudes, we have angles, so it's all related. And if we rearrange it, we get that the inner product between x and y is the cosine of the angle between them times their magnitudes. So all of this information is interrelated. And right, so the scalar product gives us information about the angle between x and y and the magnitudes of x and y. So if you have any three of these pieces, so if you know the inner product and you know the magnitudes, then you can solve for the angle. And similarly, like if you know the angle and you know the magnitude, you could solve for the inner product. I don't know what you're doing that you need to do that, but like if you know any three, you can solve for the last one. So this is really handy, because what you'll notice is that when the magnitude of each of these vectors is 1, then it simplifies, it reduces nicely. So in the case where the magnitude of x and y are both 1, so this becomes 1 and this becomes 1. And so it simplifies to just this. And now we can quite easily get the angle between these two vectors, which is something that we do a lot in game development. So by normalizing x and y, and when I say normalizing, I mean converting it to a unit vector. So by converting x and y to unit vectors, we can use the scalar product to give us the angle between these two vectors. Are there any questions about scalar product, about unit vectors, magnitude? All right. So I said at the beginning that we were going to interlace math with code, and I forgot I said that. So now we're going to go back and implement these methods. Let me switch back over to Roblox Studio. All right, this is our vector class that we've been working on. And we're going to first add, so we already have magnitude, and now we know how to do how to unitize it. So we'll implement that. We'll take in a vector, and then for most important that we take and we divide it by its magnitude. But you might take issue with this, and that's because the magnitude could be 0. And if the magnitude is 0, then we're going to return something that's like something really awful, like each going to be infinity or something. So we might as well also check that the magnitude is not 0. So let's just save the magnitude here. We'll check that the magnitude is greater than 0. And then we'll return this. All right, and if it's not greater than 0, then we'll maybe we won't throw an error. Actually, the confusing in our class is that we're actually just going over 0 vector. That's going to be right. Like the point is that if everything goes well, if the magnitude of v is non-zero, then we'll return back with magnitude. And if something goes wrong and the magnitude is 0, then we're just going to return the 0 vector. And I'm actually going to change this up a little bit. I'm not going to check that it's greater than 0. I'm going to check that it's a small number. So I've set tolerance here to be a really small number. What this notation means is that 1e negative 13. This is 1 times 10 raised to the negative, which is like this is a very small number. And the reason I'm doing this is that if we take v and we divide by a very small number, we might get some floating point issues. That's all that is, dealing with floating point. So that is unitizing a vector. And next, we do the angle between two vectors. Take in two vectors, and let's also copy over our type checking. And what we said is that the angle between two vectors, so first we need to unitize them. Right, I keep saying unitize. Normalize is, I think, a better word. So we'll normalize them. We've like gotten rid of the magnitude information, and now we're only left with angle information. And then it's going to be the arc cosine of A dotted with B. There's like, so because we're not covering trigonometry or algebra 2 in this course, I won't like explain too much why you need to do this, but it's actually very important that you clamp this between -1 and 1, because the arc cosine function takes in an input between -1 and 1, and it could happen, like in theory, our dot product should give us a number between -1 and 1 because we used unit vectors. But because of floating point issues, again, it could fall outside of this range. And so we're just going to clamp it to -1 and 1. So you also may be familiar with another way of computing the angle between two vectors, which uses cross and dot. We're not going to, we won't use that. All right, before I switch back over to the notes, are there any questions about the code I've written? All right, good. I guess one last thing, we might as well check. This is greater than 0. Or sorry, if either of these are 0, then it doesn't make sense to take the angle between them. Not even sure. Maybe we'll just error. All right, switch back over to notes now. And by the way, we've not like proven this to you yet. This should still be like, you should still be thinking like, why does that work? It is an optional homework exercise, and I'm sure Aiden will release a solution next week. All right, so we have magnitude, we have unit vectors, we have angles between things. Now we can get to projection. So given any two vectors, we can find the orthogonal projection of x onto y, and this answers the question of how much of x is in the direction of y. I think that there are two perspectives on this. The perspective, which I quite like, is that a projection of x onto y is like looking at the shadow of x onto y. So like we have our sun up here, and our sun is light rays, and light rays are going perpendicular to y, right? And the projection of x onto y is the shadow of x. And we'll write this as projection of x onto y. That's our notation for this course. This is how I like to think about it. Just kind of makes sense. It's nice. It's the shadow. But then mathematically, we formulate it as a minimized problem. And the problem is, so we're going to look at every scalar multiple of y, and we're going to look at the distance between this vector and x. So here's a scalar multiple of y, and we're going to look at its distance. We're going to ask, is this the minimal distance between x? And the answer is no. And we'll look at this one too, and we're going to say, okay, is this distance the minimal distance between x? The answer is no. Okay, we can keep doing this, and we're going to do this for every single scalar multiple of y. And even the ones going the other direction, every single one. So we're going to check against every point on this line. And the projection is the one that minimizes this distance. So this one is a little more confusing, but it's because we can use the mathematical definition to actually compute the formula for the projection. So mathematically, we have two pieces of information. We know that the projection of x onto y is going to be some scalar multiple of y, meaning the projection of x onto y it's going to lie on this line. This is one piece of information we have. And the other piece of information we have is that when we look at this vector between x and the projection, it's going to be orthogonal to y. That's what this is encoding here. That the inner product between these and these are 0, meaning they're orthogonal. And then the upshot to all of this, I didn't write out the computation, but the upshot is that this alpha, the projection of x onto y, is the inner product of x and y divided by the inner product of y with y times y. And we're now going to rearrange something a little bit. Actually, I'll write it over here. Okay, so at the very beginning, we defined magnitude. We defined the magnitude of y to be the square root of the inner product of y itself. So all we're going to do, we're going to look at this and we're going to say, okay, so this is actually the magnitude of y squared. So this is equal to xy over the magnitude of y squared times y again. Okay, and then we're going to split up that magnitude on the bottom. So we'll put one of them in front, and then we'll also put one of them under y. And then if you did your homework last week, we know that we can bring this into the inner product. So this becomes the inner product of x with y over the magnitude of y times y over the magnitude of y. So now this is the normalization of y. This is y with magnitude 1. This is y with magnitude 1. So the way I write it out in code is that this is equal to x dotted with y dot unit. Oh, I've run out of space. Times y dot unit. The y dot unit, this is this y dot unit is this. So this is how we project a vector onto another in code. And we'll do that right now. All right, so we're going to write a project onto. I'm going to take in two vectors, and we will just copy over what we just wrote. So it's going to be a dotted with b unit times b unit. Yeah, and I guess we should also copy over our type checking. If we really care about performance, maybe we'll also put this into a variable. All right, now we have our projection function. Okay, so that rounds out our geometric methods that we're adding to our vector library. And Next, we're going to build towards the Holy Grail Gram-Schmidt algorithm. So sometimes we want to project onto more things than just another vector. Sometimes we want to project onto dimensions of objects of higher dimensions. So how do we project onto a plane? So the orthogonal projection of x onto a plane asks a very similar question, but I've worded it a little bit differently. It asks, how much of x lives in the plane? So what do I mean by this? So like intuitively, we understand what the projection looks like. So I'm just going to draw it. So we're going to project x down onto the plane. And here's its projection. So this is going to be the projection of x onto the plane. What I mean by like the amount of x that lives in a plane is that we can decompose x into the sum of this vector and the sum of this vector. So this down here, this vector lives in the plane, this vector is perpendicular to the plane. So the amount of x that lives in the plane is this vector down here. And we can even do this for think about a four-dimensional vector project dimensions or any dimension lower. Right. So before I get to the point, we have to make a little bit of a detour and talk about subspaces. So roughly, a subspace is a Euclidean space that lives inside of another Euclidean space. So in R3, can somebody give me an example of what they think is a Euclidean space living inside of R3? A cube. That's a good answer. It's close, I think. Like if you like take your cube and then you like expand it infinitely in every direction, and then you just get like R3. So it's like it sounds kind of curt, right? Like R3 is a subspace of R3, even though it's like the entire space, we still call it a subspace. The reason it's not just strictly a cube is because you could take two vectors that live inside of the cube, and you can add them, but you can end up with something outside of the cube. That's not like a closed space. Whereas vectors in R3, you add them, you get back something in R3. Right, does anybody else have some thoughts? All right, I'll give you one. Line. A line is a subspace of R3, specifically a line going through the origin. This is a Euclidean space. It's kind of like R. It's kind of like the real numbers, but it lives inside of R3. And then we can also have a plane. So here's a plane, and it goes through the origin. And this is kind of like R2, but living in R3. And then the last subspace that you could have is just the origin, an empty point. It's kind of like a boring subspace, but it is a subspace. Are there any questions about this? Okay. So now we'll talk about how do we like mathematically write out a subspace. And I promise this is all getting back to, we'll get back to projections at some point. So the way we write out a subspace is as the span of a set of vectors. So we have a set of vector 1 through yk. Notice the superscripts. The superscripts mean they're not coordinates, they're vectors. So we're going to take these vectors, and the span of these vectors is going to be the sum of all scalar multiples. So like, okay, what do I mean by this? So a line, we'll just start with one vector. Call this x. And the span of x is going to be all of the scalar multiples of x. So make x bigger, We can make x really big, we can make it smaller, we can make it go in the other direction. And so the span of x is this line. It'd be great if it went through. Let's see, there we go. So we would write this as the span of x. And then for a plane, so we'll write out two vectors. So we have x and y. And so a sum of scalar multiples, so we could just do x and y. We know how to do this. So this point out here, this is probably x plus y, but we can also take different combinations too. So we could take 1, 2, 3. Right, so like this is going to be 2x, roughly 2x plus 3y. And we could come over here, do something like this is negative 2.5y minus 1/2 x. I don't know why I mixed decimal and fraction. Negative 3/2 y minus 1/2 x. So you do all of these combinations. You do every possible combination of scaled amounts of x and y, and you get a plane. How do I? How this is so messy. Let's see. This is my plane. Okay. So this plane. This is the span of x and y. Okay, so like what is the point? So it turns out that it's like that there are like ideal conditions for projecting a vector onto a subspace. And I have a word on here that I've not defined yet. So these two vectors x and y, they're that x and y a basis. The technicalities for when something can be a basis. For instance, we had the vector y and another vector going in the opposite direction. Obviously, you take combinations of these, you don't get a plane. And so these two vectors could not be a basis for the plane. Well, maybe it's not worth getting into. Anyway, the point is that in order to do the project of the plane, we're going to need in the plane, like we need some data in the plane so that we can project onto it. And specifically, we need an orthonormal basis for the subspace. If we don't have an orthonormal basis, Aiden went through on Monday, things break. So when I say orthonormal basis, what I mean is that on the last slide, those two vectors, x and y, they ought to be perpendicular. So they're orthogonal, and then they're orthonormal because these have one. Okay, so like kind of a scuffed explanation for an orthonormal basis. Basis is a set of vectors that spans a subspace where the vectors are mutually perpendicular unit length. And so our saving grace is Gram-Schmidt. This Gram-Schmidt algorithm will give us an orthonormal basis for a subspace. We just need to give it some vectors, and it'll spit out an orthonormal basis. Okay, I hope we all feel very sufficiently motivated now. All right, let's get into the code. So I think, yeah, that was my last slide. How can it turn non-orthonormal vectors into orthogonal ones? Okay, yes, I will explain this right now. The best way to explain Gram-Schmidt is to just look at it. It's kind of tough to parse mathematically. So I'm just going to show you Gram-Schmidt, and then we'll code it. And I think this is better than looking at symbols. Okay. So here we have three vectors. These are actually, I'm just going to randomize it until it gives good looking vectors. Okay, these look pretty good. So these are three vectors. They're clearly not orthogonal to each other. They're not unit. length, and we're going to use Gram-Schmidt to turn them into an orthonormal basis. All right, so the first step is we're just going to pick a vector. And, well, kind of like the first one's free. We just normalize it, and there's our first one. There's our first unit length vector. So that's pretty easy. So we just pick a vector, and we make it unit length, and there it is. So first step is done, pretty easy. And then we'll go into the second step. Okay, so we're going to pick another vector, and this time we're going to project it onto the first vector. So we took our light bulb and we found the shadow, this red vector, onto this green vector, and that is the blue. So we took a vector, we projected it, and now we're going to subtract away the blue vector and get this. So the point is, we take a vector and then we subtract away the amount of this vector that's in the direction of green. And we end up with something perpendicular to green. And then lastly, we just normalize it. All right, so this is pretty great. We now have two vectors which are orthogonal to each other at their unit length. Now we just have to do it one more time. So that step is done. We'll go into the next one. We're going to pick the last vector. All over the place. So we're going to pick the last vector, and we'll repeat a similar process. So we're going to project it onto the first one. We project red onto the green, and then we're going to subtract away this amount. So we subtract it away, and then we'll do it again. So now we project onto our last vector. We subtract it away, and then finally, normalize it. And we're done. I agree, Borg. I think it's pretty awesome. Yeah. Gram-Schmidt is great. I don't know if I have enough context to be as bold as Aiden to say it's like the greatest algorithm in linear algebra, but like it has certainly been helpful to me in my coursework of like just the existence of Gram-Schmidt, that you can do this and take any three vectors. Well, there's some like, it's not any, there's some conditions on that, but we can take three vectors and turn them into an orthonormal basis is pretty great. John, that's a good question. We're gonna get to that soon. John asks, what are some applications of this in game dev? So we'll get to that. Borb asks, so these are the closest orthogonal basis that the vectors can represent. The answer to that is probably not. I guess that's hard to quantify, like which are the closest. But there are better algorithms for that if you care about. Okay, how am I doing on time? Are we going to run out? Okay, we have 12 minutes. I think we can get through everything. So I'm going to run through it very quickly. I'm just going to like click through it so that we can kind of get the vibe of Gram-Schmidt. So we're going to pick a vector. We're going to normalize it. And then we're going to pick a vector, project, subtract, normalize. And then pick a vector, project, subtract, normalize. That's the process that we're following. All right, now let's code it. Oh no. All right, let's start with a new Gram-Schmidt method. And we're probably going to need, are we going to need vector? Yes, we're going to need vector. Okay, so we'll require vector. And we need a function, Gram-Schmidt. And Gram-Schmidt is going to take in a list of vectors. We'll return our Gram-Schmidt. And then what we're going to want to end up with is a table of orthonormal vectors. All right, so what was the first step in our process? Thank you, Neptune says they like the keyboard ASMR. I was hoping that the keyboard wouldn't make it this lecture, but I guess it will. All right. So our first step in the process was like we just take the first vector and normalize it. It's kind of like free. So the first orthonormal vector is we're just going to take the first one and we'll just make it unit length. And you might take issue with this. We're going to come back to it. So there's an issue with this here is if the vector is the zero vector. If it's the zero vector, then we can't normalize it. But we're going to get to that. So we're just kind of like going through the same demo but in code. All right, so then the next step is we're going to take the second vector and we're going to project it onto the first one and then subtract that away. So our second orthonormal vector is we're just going to take the second vector and we're going to project it onto the first vector, the first orthonormal vector, and then unitize this. No, we're not doing that. I got a little ahead of myself. Sorry. So we take the vector, we subtract away the projection, and then we unitize it. All right, so this is the process, and I'm not going to belabor the point. So now we're writing a for loop and do it. So we're gonna do this for every single vector. Really, maybe I'll just so for each vector in the vectors list, the first thing we're going to do, I should probably assert that the vectors is a table of 3 vectors. Not necessarily. Okay, maybe I wasn't clear. You can do Gram-Schmidt on any amount of vectors, and you can do Gram-Schmidt on vectors of any dimension. So we are not just limited to R3, which is like really great. This is one of the amazing things about Gram-Schmidt, is that it works for all vectors in all dimensions. All right, so we're going to go through each vector, and then we're also going to go through each of our orthonormal vectors, and then we're just going to subtract away the projection of our vector onto the orthonormal vector. Okay. And now the last thing we have to do is normalize it. So, and we'll just insert into our orthonormal vectors table the vector of unit length. Well, not quite. Because there's an issue of again, what if the vector's magnitude is 0? So we might as well throw in a check for that. All right, so if the vector's magnitude is now 0, or we'll do the same thing that we did for our vector class. Add in some really small number here. So if the magnitude is greater than some small number, then we'll normalize it and add it into our orthonormal vectors. Yeah. So what does it mean if our magnitude ended up 0? What it means is that we have a case like this. Let me set my demo. It means we ended up with a case where we have say we've selected this vector here, and it is spanned. It is it belongs to the plane that these two vectors span. Just extraneous information. We already have these two vectors spanning a plane. We don't need a third one. And so that's what it means when this one ends up being magnitude 0 is it was in that span. Magnitude will be 0 when 2 of the vectors exist in the same line. Yes, that's also true. Yeah. So if in this case as well, these two vectors are roughly on the same line, and so one of them will not make it. It will not survive. All right. So there's really nothing to write here. We're just not going to add our vector. Okay, and then at the end of it, we just return orthonormal vectors, and I'll get rid of these two as well. So this is Gram-Schmidt. It's quite simple. We take a vector, we project it onto the orthonormal vectors, subtract that projection away, and then we normalize it. All right. Now I promised John, I promised you an application of this in game dev, so I'll show you that now. So I have some demos here, and by the way, all of this code is on the GitHub, so you can go through these demos too yourself. Okay, right, before I move on, Borb asks, what are the consequences of returning less vectors? Well, for one, I'd say like it's consequences is like strong. It's not like a, well, it's not a bad thing. What it means is that we had like extraneous vectors, like we didn't need all of our vectors to span the subspace. And like what this gives us, so like if I chuck in a set of vectors and I get out less vectors, what it means is that the dimension of the space spanned by those vectors was, well, how do I put this? Like if I put in n plus 1 vectors and I get back out n vectors, then that means that the dimension of the space spanned by those vectors is n instead of n plus 1. I think I just gave away a homework question. That was my bad. Okay, right. We've got only a few minutes left, so let me show you an example. Actually, I think it'll be easier if I, yeah. Okay, so the example is C-frames. So like C-frames, we know that they have a look vector, they have an up vector, and they have a right vector. And in all of our experiences, these vectors have always been orthogonal and they've always been unit length. But it turns out you can kind of just give a C-frame like whatever numbers you want and just like take them. So you can totally have C-frames whose right, up, and look vectors are not orthogonal and they're not unit length. And so I'll demonstrate that here. So we're going to start with some C-frame, just some random C-frame. And then we're going to multiply B by the C-frame 1,000,000 times. And we're just going to see what we get. So we're going to run this. This is, hold on. Let me do this again. Okay. So the C-frame that we started with A, the angles between all three vectors are roughly 90 degrees, 90 degrees, 90 degrees. And then C-frame B, after we multiplied it like 1,000,000 times, we noticed that the angles are not exactly 90. So we're starting to stray away from our orthonormal basis. And the same thing goes for the lengths of all the vectors. So the lengths of all the vectors are not quite 1. But we can actually do like way worse than this. And when I was doing this, it was like really funny to me how bad you can make a C-frame. So we'll do this 10 times. So we're going to update B, and then we're just going to keep multiplying it by itself over and over and over. And I'll actually just use fixed numbers instead of random. Okay, so we'll run this. And what do we see? Okay, so still roughly 90-degree angles, roughly unit length. And we'll do it again, so we'll multiply it 20 times. Okay, it's getting a little worse. How about 30? Oh boy. Okay, now the angles are 180 degrees and the lengths are God knows. Yeah, so you can accumulate error doing this very quickly. So the point of all of this is that you end up with some really awful C-frame, but then you just run Gram-Schmidt on it and it's okay. We can return to our orthonormal basis. And by the way, I have it here. Yeah, so Roblox actually has a function to do this that'll take a C-frame and orthonormalize it. It doesn't use Gram-Schmidt. It uses a different method because it's supposed to be used incrementally. So it's like really, if I wanted to use this method, I should do like B orthonormalized. So I do it one at a time. So like Roblox has a method for this. It's not quite Gram-Schmidt. And actually, if I even tried running it right now, I don't even think it would give me an orthonormal basis. Like Gram-Schmidt is, oh, now it's gone. There's no undo. Uh-oh. No, I did it again. Okay, the point is, Roblox's orthonormalized function will actually, and sometimes it won't give us an orthonormal basis, but if we do Gram-Schmidt, we probably will get one. All right. Right. So that John, that's an example in Roblox. I'm going to show you one more. So I'm out of time. But I have one more example. Oh no, I lied. This is not an example of Gram-Schmidt. I was supposed to show you this earlier. This is an example of projection. So this is maybe you can tell by the place file. This is an old file. So I have these turrets here. I should have picked like a less violent example, but these turrets, their goal is to look at me as best as possible. So like they're all constrained by this plane, but it's still trying to look at me as best as it can. And so the way that this works is that it's like drawing a vector towards me and then projecting that vector onto its plane of rotation. So, well, I wish I had like some arrows that I could draw, but like this green turret here, it's drawing a vector towards me, and then it projects onto its plane. An example of using vector projection. All right. So we've covered the magnitude of a vector, normalizing a vector, vector projections. We've covered subspaces and Gram-Schmidt. So this is the end of lecture, and you can feel free to ask questions about any of this now.